Hello students. So in the last class we have discussed what is the supremum and infimum of a sequences. So that is finding the greatest lower bound and least upper bound of a sequences. Now we shall move on to the limit of a sequence. Already you have studied what is limit of a function, how to find the limit. Okay, now we shall see what is limit of a sequence. So the definition of limit of a sequence goes like this. A sequence AN is said to tend to a limit L. A sequence AN is said to tend to a limit L as n tends to infinity if given epsilon greater than 0, however small, there exists a positive integer m of epsilon. So there exists a positive integer m which is depending upon epsilon. So we write it as m of epsilon such that modulus of an minus L is less than epsilon for all n greater than or equal to m of epsilon. See, a sequence is said to tending to a limit L as n tends to infinity if for given epsilon greater than 0, however small, there exists a positive integer m which is depending on epsilon such that when you take the modulus of an minus L is less than epsilon, this happens for all n greater than or equal to m of epsilon. So if this condition is satisfied, then we say this sequence is tending to the limit L. Okay, so in symbols we write limit as n tends to infinity an is equal to L. Limit n tends to infinity as an is equal to L. So this is the limit of a sequence. Okay, now based on this definition, we will solve some examples. Okay, so first example is the sequence f from n to r. Sequence f from n to r defined by f of n is equal to sequence 1 by n. Defined by f of n is equal to sequence 1 by n. So our sequence is 1 by n. As the limit L is equal to 0. As the limit L is equal to 0. So we shall prove this now. So what we have to show, limit as n tends to infinity 1 by n is equal to 0. Means this sequence is tending to a limit 0. Now we have to prove this. Okay. So let us go to the solution. Now for given epsilon greater than 0, there exists a positive integer m such that modulus of 1 by n minus 0 is less than epsilon for all n greater than or equal to m. So this is by definition of limit of a sequence we have written. Okay, so for given epsilon greater than 0, there exists a positive integer m such that modulus of an minus L. So your an is 1 by n and L value is 0. So 1 by n minus 0 is less than epsilon for all n greater than or equal to m. So this is by the definition of limit. Okay. Okay. Now when we simplify this, modulus of 1 by n minus 0. So you get only modulus of 1 by n and 1 by n is positive. So we can write it simply as 1 by n is less than epsilon. Okay. Next we have n greater than or equal to m. N greater than or equal to m. Now when we take the reciprocal of it, that is 1 by n becomes less than or equal to 1 by m. N greater than or equal to m, when we take the reciprocal of it, it becomes 1 by n is less than or equal to 1 by m. Okay. Now 1 by n is less than epsilon. So that implies 1 by m is less than epsilon. Why? Because see, we have 1 by n is less than or equal to 1 by m. Means what? 1 by m is greater than or equal to 1 by n. But 1 by n is less than epsilon. Therefore we get 1 by m is less than epsilon. So if and only if, so this happens if and only if m is greater than 1 by epsilon. Okay, so 1 by m is less than epsilon if and only if m is greater than 1 by epsilon. Now thus for epsilon greater than 0, and integer m greater than 1 by epsilon exists. So for epsilon greater than 0, we get the m value which is greater than 1 by epsilon. So this value exists. Hence for this value of m, modulus of 1 by n minus 0 is less than epsilon holds. For this value of m, modulus of 1 by n minus 0 is less than epsilon holds. So this proves that limit as n tends to infinity 1 by n is equal to 0. Okay, so this must happen for all n greater than or equal to m. Means for given epsilon greater than 0, there exists a positive integer m such that this condition has to be satisfied. Now m greater than 1 by epsilon exists for all epsilon greater than 0. See, for all epsilon greater than 0, there exists m, and for this value of m, this condition holds. Therefore, the limit of 1 by n as n tends to infinity is equal to 0. Okay, next we shall move on to next example. So using the definition of limit, show that limit as n tends to infinity 3n minus 1 divided by 4n plus 5 is equal to 3 by 4. Now we have to show the limit of 3n minus 1 divided by 4n plus 5 as n tends to infinity is 3 by 4. That we have to show it using the limit of the sequence. Okay, now we shall see the solution. So let epsilon greater than 0 be given. Now we have to show that there exists m such that modulus of an minus 3 by 4 is less than epsilon for all n greater than or equal to m. See, for given epsilon greater than 0, we have to show there exists some integer, positive integer m such that this condition holds good. Okay, now what is our an value? An is 3n minus 1 divided by 4n plus 5. Now we shall substitute here the an value. So we get modulus of 3n minus 1 divided by 4n plus 5 minus 3 by 4 is less than epsilon. Now cross multiplying this, so we get 12n minus 4 minus 12n minus 15 divided by 4 into 4n plus 5. So when we simplify this, we will be getting this. Now this is less than epsilon. Now 12n and 12n will be cancelled. So minus 4 minus 15 is minus 19. So we get minus 19 divided by 4 into 4n plus 5, which is less than epsilon. Now negative number under modulus, it becomes a positive number. So we get 19 divided by 4 into 4n plus 5 is less than epsilon. Okay. Now when we simplify this, so when we send this 19, this comes to your denominator, and we'll be sending this 4 to the side. So we get 1 divided by 4n plus 5 is less than 4 epsilon by 19. Okay. Now taking reciprocal, we get 4n plus 5 is greater than 19 by 4 epsilon. Okay. Now sending this 5 to your right hand side of your inequality. So we get 4n greater than 19 by 4 epsilon minus 5, which implies, so sending this 4 side, that becomes 1 by 4. So n is greater than 1 by 4 into 19 by 4 epsilon minus 5. Okay. Therefore we choose m value such that m is greater than 1 by 4 into 19 by 4 epsilon minus 5. So we got n is greater than this value. Now we will be choosing the value of m such that m value is greater than this value, because n value should be greater than or equal to m. Okay, so we will be choosing the value of m such that m is greater than 1 by 4 into 19 by 4 epsilon minus 5. Then for all n greater than or equal to m, we have 3n minus 1 divided by 4n plus 5 minus 3 by 4 is less than epsilon. Okay, therefore limit of 3n minus 1 divided by 4n plus 5 as n tends to infinity is equal to 3 by 4. So your next example is using the definition of limit of a sequence, show that limit 2 plus minus 1 to the power of n divided by n is equal to 2. Okay. Now let see the solution. So for given epsilon greater than 0, we have to show that there exists m, a positive integer m, such that this condition holds. That is, modulus of an minus 2 is less than epsilon for all n greater than or equal to m. Okay. Now we have modulus of an minus 2 is less than epsilon. What is an? 2 plus minus 1 to the power of n divided by n. So we shall substitute that. So we get 2 plus minus 1 to the power of n divided by n minus 2 is less than epsilon. Okay. Now 2 and minus 2 will get cancelled. So we have modulus of minus 1 to the power of n divided by n is less than epsilon. Now minus 1 to the power of n value will be either plus or minus 1. So under modulus it becomes positive 1. So we get modulus of this value is nothing but 1 by n. So 1 by n is less than epsilon. That is, n is greater than 1 by epsilon. Now n is greater than 1 by epsilon. So we have to choose the value of m such that m is greater than 1 by epsilon. Why? Because n is greater than or equal to m. Since n is greater than 1 by epsilon, your m value must also be greater than 1 by epsilon. Okay. Thus we have for every epsilon greater than 0 a natural number m such that modulus of an minus 2 is less than epsilon for all n greater than or equal to m. This condition holds for all n greater than or equal to m. Therefore, limit as n tends to infinity, 2 plus minus 1 to the power of n divided by n is equal to 2. So limit of this is 2. So next example is show that the sequence f from n to r given by f of n is equal to n does not have a limit. So we have to show this sequence does not have a limit. Okay. So we will prove this by contradiction method. What is contradiction method? So we will be taking that limit means this sequence has a limit L and we will arrive at a condition as a contradiction. Okay. So first let us take limit as n tends to infinity of n is equal to L. So if limit of this is equal to L means then for every epsilon greater than 0 there must exist a positive integer m such that this condition has to hold good. That is, modulus of n minus L is less than epsilon for all n greater than or equal to m. Okay. So when we remove the modulus of this, we will be getting minus epsilon is less than n minus L, which is less than epsilon. Okay. For all n greater than or equal to m. Now we will add L throughout this equality. So we get L minus epsilon is less than n, which is less than L plus epsilon for all n greater than or equal to m. So thus for all values of n, however large, lie between L plus epsilon and L minus epsilon. Now for all means all values of n, however large it may be, it lies between the range that is L minus epsilon and L plus epsilon. This is false, and the contradiction shows the sequence n does not have a limit. So this is a contradiction statement. Okay. Therefore what we have assumed that this sequence n has a limit L, but we are arriving a contradiction statement here. Therefore this sequence n does not have a limit. Okay. Now we shall discuss some more problems in the next session. Thank you.